So I'd like to talk about voice AI at large, in particular things that we've been doing in the past 18 months at Kyutai, which is this fairly recent lab started end of 2023. It's a non-profit open science lab dedicated to foundation models, in particular multimodal foundation models. And today I will focus really almost exclusively on text and speech with a drop of image at the end if time permits. All right. So first of all, let me start by a few motivations for working on voice AI and speech-based models. One of the main reasons are related to the fact that voice interactions are very rich in terms of meaning, but also beyond the meaning, there is all the emotion, the intent of the people, the empathy, etc. when people talk to each other, and it's also it's a very efficient way to at least to communicate things in a very lively manner. Certainly more than with text, and also it's very inclusive in the sense that some people don't know how to read or write, and yeah, most people can speak and listen. When it comes to the interaction, either with a machine or using a machine with other people, because of the reasons I just mentioned, being able to interact or to use the speech channel for the interaction is very efficient, and it can be very practical. There are many use cases where using keyboards and screens are not an option. And so that's why it's becoming more and more important to have voice technologies. It's even a very old topic, speech-based interaction, and it does cover a number of things. The first one I will talk a lot about today is spoken dialogue with the machine through speech only, but there are other technologies related to that, and I would say a few words about them. One is speech to text, that is transcription, or the dual problem, which is speech generation, and there is also translation. So there are a number of things where voice and speech play a very important role. But let me start with spoken dialogue. So here the idea is really to talk with the machine only with voice. So it goes both ways for the user and the machine. And the way it's done in most systems still to date is what is called the cascaded approach, which is fairly natural and works pretty well. It's effectively a chaining of different modules, which are all based on neural networks these days, and they're all very very accurate with modern AI. So it starts with the so-called voice activity detection to decide whether the user is speaking or is done with speaking, and then what the user said is turned into text using an automatic speech recognition system, ASR in short, also called speech to text, STT, and then the text goes into your favorite text chatbot, so a large language model, and then the answer of the AI, which is text as well, is turned into voice using a text-to-speech generation, also called TTS. So this works fine again, and it can use on-the-shelf tools, but it has a few drawbacks. The first one is the latency, because you have to really chain the different modules, so it can be a bit long, although, as I will say at the end, it can be optimized to some degree. But so this is mostly engineering. But there are two other limitations which are more fundamental. The first one is the fact that by transcribing into text what the user says, you are mostly losing all the paralinguistic, meaning all the nonverbal, the emotion, the accent, the timbre, etc. So all the prosody. That's one thing. And the other thing is the fact that you have to impose terms of speech between the machine and the user. So effectively, it's fairly slow, it's not very rich in terms of paralinguistic, and it's tone-based. And in particular, regarding the last aspect, having turn-based conversation is completely fine, but essentially it amounts to talk with the machine through a walkie-talkie, which again is exactly what you need in many cases, but you have essentially to switch on and off the mic and decide who is talking. So it's very contrived, not very fluid and natural, and it's called, this approach is called the half-duplex. Ideally, what we would like to have with the machine is what we have with other people, whether we are talking face-to-face or through a telephone, is what is called the full-duplex. So you see that the two interlocutors, they can overlap, there is back channeling, and this is not only useful for the efficiency and the rapidity of the interaction, but also for the richness, because by emitting small by having some back channel reactions, etc., it's also a way to interact and to indicate that one you agree or disagree, etc. So there is a lot of advantage in this full duplex approach, but technically speaking, it's not compatible with what I just showed before. So one thing that we attacked at Kyutai at the very beginning is this barrier in spoken dialogue systems. Okay, so how to do that when you want to have a speech audio model? A very natural way to go, because speech at the end of the day is like text but it's spoken words as opposed to written words, is to capitalize on the fantastic progress of large language models, which are text-based. So essentially, you could take your favorite text large language model architecture and see whether you could use it almost as search for speech. But the first obvious difficulty that you have to face is the fact that speech, not only it's uttered words, but it's also an audio signal. So essentially, there is a lot of data or signal that you have to absorb. In particular, if you think of this small sentence of 3 seconds and 8 words, Kyutai is an AI lab based in Paris. If you have a sort of standard 24 kilohertz sampling, then you end up with more than 70,000 samples to be fed to your transformer. So if it's a mid-sized transformer, this is absolutely impossible due also to the quadratic complexity of the attention mechanism. So typically, by having these samples are as units, then you have 10,000 more tokens, which amounts to 100 million more cost or computational cost in the self-attention. So this is prohibitive. So the first thing that you need if you want to have an audio-only language model is to first of all compress and tokenize your audio stream with something which is at the same time slow enough not to clog the transformer, and at the same time rich enough to capture what is said by the user and to generate good quality speech for the machine. And if you manage to have such a tokenizer or audio codec, then you can train it in the same way as you train an LLM, or pre-train rather, by training it to continue a large amount of audio that you have downloaded from the internet. And effectively, this is something that we did. So there is already a number of works aiming at that. So we building on the literature, in particular works from Google and Meta, we built our own audio codec called Mimi, which is exactly done for this purpose. So Mimi works as follows. So it's a causal neural codec based on both convolution layers and also a transformer bottleneck. And what it essentially does, it takes the audio stream like the waveform and turn that into at a frame rate of 12.5 hertz. So each frame time frame now is 80 milliseconds, and at each of these time instance, you end up with a representation which is a continuous representation at first, but then which is turned into something quantized, and this representation is quantized hierarchically. So it means that typically at a given instant here, if you look at my laser pointer, you have a stack of tokens. These tokens are vectors taken from code books. And the first level is mostly semantic, and the other, the upper levels here, I represent 3 of them. Effectively, there are at least 8 in total. They are more and more detailed in the acoustic domain. So at any instant with the full stack, you can re-decode something which capture very well the prosody, the voice, also the ambient noise, and the meaning of the speech. So this is what we use, and in order to train this codec, it's essentially based on the idea of the vector quantized VAE, but there are also other aspects, in particular some adversarial loss in the training, and also we use distillation from another audio codec or speech codec, which is mostly semantic and which is non-causal, but we distill that. That's the Wave LM from Microsoft, and we distill that into our hierarchical causal codec. Right. So now we have this representation. Let's go back to the language model that we can try and learn on top of it. So this is what we want. At each instant, we have the transformer, the decoder-only transformer, to be able to predict the new stack of audio tokens, given the sequence of the previous tokens. But now we have this problem that at each time frame we have not one but a hierarchy of tokens. So there are different ways to approach that. The first one, which is a bit naive, but is to flatten things. So essentially, if you have 4 tokens in the hierarchy, it means that you flatten that into a sequence of 4 tokens, and you do that again for the next time slice, etc. If you do that, and then you predict the next token, etc., etc. So if you do that, the complexity is still quite high. So typically for 1 second of audio, you still have 100 forward passes in your mid-size transformer, which is still quite expensive. So instead, what we did is to not to flatten, but to squeeze things. So we essentially sum up the 4 or the 8 audio tokens at a given instant. And then we ask the temporal transformer not to predict right away the next 8 tokens, but something intermediate, which we call the temporal context embedding. And this embedding, which is 1 vector, is then decoded into a sequence or hierarchy of acoustic and acoustic and semantic token with another transformer, which is way smaller, and that we call the depth-former, and which essentially, produce then, in this case, the 4 audio tokens. The first one is semantic and the other one acoustic, and then they can, this is complete for this time frame. We can move on. So this is essentially what we have as an architecture. So it's compound. You have a large temporal transformer, and on top of that, at each instant, you have a small transformer in charge of unfolding the temporal context into a full hierarchy of audio tokens. So with that, the complexity is further reduced, and it turns out to work very well. So now we can train these architecture. So it's composed again of a neural encodec called MIMI and this compound transformer that we call the RQ transformer. And we can train that or pre-train that for continuing raw natural audio in English with the classic autoregressive approach. And already that allows to get a very promising speech-only continuation that I'm going to let you hear, and hopefully you can hear something. So I'm going to play a prompt, which is an actual real audio, and then I will play the same thing but with the continuation used that is produced by the autoregressive audio language model that I just explained.
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting.
Did you hear something, Bertrand?
Yes.
Oh, what a relief. Okay. Now, again, the same thing, and you will then hear the continuation.
Listen to your sister, Morty.
No.
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting, entangled in the ether. You don't think so? All right, fine, then listen to your sister. Do you want to make it in the world, they're going to die alone with nothing but their kindness.
So as you can hear, the voice, the speaking style, everything is well continued, but this is only a pre-trained model. There is no capacity of dialogue. There is no reasoning or knowledge whatsoever. But it really shows that the model is able to do this speech continuation task, and this is what matters. And now we have to harness that with a proper fine-tuning. All right. So. Now, when we want to go from this continuation model to an actual dialogue, then we have another problem, which is that at run we need to have two speakers, the AI and the user. And one way to do that, which comes back to this half-duplex walkie-talkie thing, is to interleave in the audio stream user and AI, depending exactly in the same way you have with the text chatbot. Okay, so that's pretty natural, and it can work fine, but it missed the goal that we set for ourselves with full duplex. So in order to go full duplex, what we do instead is we put in place two distinct and parallel audio streams, one for the user in blue and one for the model in green. And at any instant, the Archi transformer is consuming both streams to continue both streams. This is what you see here. So given the history, the past of both streams, then we produce the new audio tokens for the AI, the new audio token for the user, and we continue like that, which essentially means that at both the user and the AI can talk at any moment. There is no user turns here, or speaker turns, sorry. So to recap, the model looks like that. We have the two audio streams, one in blue for the user, which is essentially fed from the what the user says and goes to the encoder part of Mimi, and this part is continued, but never, well, not the continuation is not used because it's essentially teachers forced, and there is no need of decoding. Conversely, in green, you have the audio stream for the model, and this one is the one producing the answer of the speech of the model, and it's decoded to the waveform using the decoder of Mimi. Beside these two streams, we have added another stream, which is a text stream with a text token, which are aligned along the temporal axis, which corresponds to the audio stream, but they are produced and they are predicted jointly. We call that the inner monologue, and this proved very powerful in order to retain all the capacity of starting pure text LLM, which is sort of the root of the all model, and starting from the text LLM, then we add the different audio stream, etc. I will explain in a minute. So this text LLM backbone is one that we built ourselves. It's called Helium. And then, it serves also as an initialization. So now you have this multi-stream, multimodal machinery, which at a frame rate of 12.5 hertz is able to produce the next audio and text token as you wish. And it means essentially that the model itself, Moshi, at any instant is jointly listening, thinking, so to speak, and talking at all times. And talking might mean emit a silent token. And this is what we wanted to achieve, so this is a full duplex capacity. And the theoretical latency here is 160 milliseconds for a technical detail that I will briefly show in a second. But we have to train this beast, which is not completely obvious. So we have first a pre-training. So there is first the pure text pre-training of Helium with 2.2 trillion tokens. Then there is the pre-training of the audio part of Moshi, but single stream. For that, we used 8 million hours of English speech, but also continuing with some text pre-training. This audio speech is actually transcribed to text using the open source Whisper model from OpenAI, and the model is initialized with the text LLM, and we do the pre-training here. Then we end up with text and audio together. And then there is the post-training where we start introducing the capacity of dialogue. So we introduce a second audio stream for the user, and for that we needed actual two-channel conversation with two people discussing on different channels. So that is not very easy to find. So we started by diarizing actual mono channel speech. So it's noisy, it's not perfect, and for that we use the Payanode tool. We did that for less than 1 million hours, and that allowed the start of the post-training to multistream, and then we did the actual fine-tuning toward really natural dialogue, and for that we needed good quality, two-speaker separated audio, and we did that in 2 steps. The first step is something is conducted using something that we found online, which is a relatively small but very interesting separated audio or speech data set, which was recorded at the end of the 20th century in the 90s on the phone. So these are phone conversations in the US. So it's called Fisher, and using that we were already able to train an actual spoken dialogue model, but it does speak as an American person on the phone in the 90s. So let me play a very quick excerpt.
Call from South Arizona.
Oh, brilliant. So you're American?
Yes.
So you know about the US, right?
Sorry?
So you know about the US?
Yes.
Okay, so who's the president right now?
The President Bush.
Oh, okay.
So it goes on and on. It also discusses about his Motorola mobile phone and his plug-in modem in his Dell laptop. So it's a very vintage. But that is, of course, not what we wanted eventually. So in order to get rid to the proper spoken dialogue system, so we moved to another step where we first of all started to record with artists in studios 200 hours of dialogue. And this dialogue, they were with different speaking styles and emotions and also types of content. And most of these conversations, which were actually, some of them were improvised, but most of them were scripted. And the scripts themselves, they were produced by our own fine-tuned text LLM, fine-tuned for and prompted for this purpose of producing lively scripts for lively two-people conversations. And these 200 hours of recordings, which is fairly small, were not used per se to fine-tune the model, but to train a two-speaker speech synthesis model, which I will talk more about later. So our own TTS. And then using this TTS, we were able to produce a lot more synthetic speech data with two people talking, so for more than 20,000 hours, including a very aggressive data augmentation with different echo, reverberation, environment noise, and gain, etc. And this is what we actually used for the fine-tuning of Moshi. So now I'm going to show a few excerpts of the system. You can still check it out online at moshi.chat. So let's start with this first quick excerpt from the official presentation exactly 1 year ago of Moshi. So what you are going to hear are the very first public words that the system said in discussions with our CTO, Laurent Mazaret.
Hello, how are you today?
Hello, can you tell me your name, please?
Hi, my name is Moshi. How can I help you today?
Hi, Moshi, can you tell me more about yourself?
Certainly. I was created by the non-profit research lab Kyutai, which focuses on using AI to tackle the main challenges of modern AI.
Okay, that sounds great.
So it's quite fast, but so a few comments both on the interface and what you heard. So on the interface, where's my pointer? So you see that, or at least it's quite small, but while the system is talking, you also see things written, and this is the output of the text stream. But again, it's not a cascaded system. It's not like text is produced and then turned into audio. The two are generated together, which means that sometimes there are discrepancies, which is interesting. And the other things are just technical parameters. And probably you have already caught the fact that the system is very responsive, sometimes answering right away, so with no latency, which is exactly what we wanted. Okay, another excerpt now, I think, with Edward Grave, so who is actually the creator of Helium, in the more classic scenario of having your voice LLM being, or voice model rather, being an assistant.
I'm going to climb Mount Everest next month, and
Okay,
I wanted.
that's incredible. What kind of gear do you need to bring?
Well, that's what I wanted to talk about, actually. What do you think I need?
Well, you'll definitely need some climbing gear. You'll need climbing shoes, a harness, a belay plate, and a rope.
Okay, I think I have all the gear that I need. So can you tell me a bit about how to prepare myself?
Sure. First, make sure your body is in shape because you'll be climbing for a long time.
Yeah, that's true. What else?
Also, make sure you have the right shoes.
Yeah.
You don't want to be hiking in sandals.
That's right.
So full of surprises, even on stage. And again, even in this example, it's even more striking the fact that the system can start answering or before the end of the sentence of the user, still being completely irrelevant. And it does make the point here that it's way more human and natural, at least, than with the cascaded systems. I'm going to skip this one. This one. This one I want to show as well. It was in a different setting, and it's exactly the point here. It's to demonstrate the robustness of the system to environment noise. One of the various advantages of the approach here is that there is no explicit, because there are no speaker turns, there is no explicit voice activity detection, meaning that there is no need for deciding whether the user is speaking or not, and also because we have trained things, which is a source of robustness. I mean, I think most of the people here on this on the call have used and be annoyed with current voice-based technologies, even the simplest ones, because sometimes it's hard to trigger the system or to stop it, and it's one of the reasons is this problem of voice activity detection, especially when there is noise and other voices around. Another aspect is because in our training data we had a lot of augmentation with noise, etc. It's fairly robust. So the very short excerpt, which is not very pleasant because it's very noisy, makes the point that it can be very, very robust to that. So you are going to see and hear Neil Zigidro talking to Moshi in the midst of a construction site.
I'm doing some construction work right now, as you can see. I'm looking for some advice. Can you help me with that?
Sure, I'm happy to help. What's the issue you're facing with your project?
So I need to build the wall and I'm a bit unsure about the proper material. What do you recommend?
Well, before we jump into that, can you tell me more about the project and what kind of wall you're trying to build?
So for the anecdote, Neil is hardly able to hear what the model is saying from the computer. And obviously Moshi has no difficulty understanding what Neil is saying despite of the sledgehammer in the background. All right. So now, this model and these models have been released last fall with a full technical paper that you can look at in particular for all the technical details and also all the evaluation details. Actually, I think probably 2/3 of the paper is dedicated to evaluation. There is, since last July, an online demo which is served on a small number of GPUs. It's at moshi.chat, so you can go and try it out for yourself. If you do that, you will notice that all the fluidity and the naturalness of the conversation is as I showed to you, although the voice is not exactly the same as the one in the public demo I showed excerpts of, because for the let me rewind. The voice that you will hear on the demo is the one that you heard. But if you use the open source model that are available on GitHub and Hugging Face, the voice is different because it's a more synthetic voice that we use in the open source for legal reasons compared to the one we have in the online demo, which is the voice of a voice artist that we worked with, but the contract was limited to the online demo. So now to the what we have open sourced. So you have two versions of the models with two voices and also different levels of compressions. In particular, so if you use the int 8 model, it runs on a low-end GPU, typically on in the cloud. But you have also a more compressed version on int 4. Which can run on a laptop. And if you go to the recording of the event of last July that I just briefly showed excerpts of, you will see at some point also Laurent Mazaret making the demo on the laptop being disconnected to the internet. So this is another aspect that we find very important when it comes also to voice-based models, is to as much as possible to have smaller models that can run on devices for both practicality or safety and privacy reasons. All right. Okay. Now let's zoom out a little bit. So in order to do this thing, we essentially built a sort of quite generic and flexible multi-stream, multimodal text audio transformer, decoder-only transformer, which is able to manipulate two audio streams and one text stream, at least in the current version. And we used it in a specific way. We trained it in order to have this spoken dialogue model with one stream for the audio stream for the user, and the second audio stream and the text stream for the model. Okay. But it turns out that the architecture can be configured slightly differently with some well-chosen time delay between the streams, and then with different ways to train the model in order to address different tasks which are voice-based. And still allowing what you heard and saw for Moshi, which is something which is real-time and streaming based. In particular, if you delay slightly the text stream and you use only one audio stream, then you can reconfigure the model and train it in order to do speech transcription while retaining all the what I just showed, for instance, the robustness to the real-time aspect, but also the robustness to the noise, etc. And so this is something that we did. And effectively, the reason why we trained this TTS in the first place, this transcription in the first place, is to help annotate our data. So now that it's something that we have actually released just a few weeks ago, we have open source our own I'd say TTS, sorry, it's a mistake, it's STT, so it's an ASR, it's an automatic speech recognition system. So if you go to our webpage, you have access to not only to the demo where you can try out this real-time streaming transcription, which is very in French and English with fairly small model. There is a 3B and a 1B, and it actually does include, by the way, a semantic activity detection, which I have not mentioned so far, but yeah. And the model is also available on GitHub. All right. And it's a useful tool per se, and it's very competitive. So you can use that as an alternative to the ubiquitous Whisper. And also, it turns out that we have also word level timestamps. So really, I think that it's very interesting for many people. We can do actually sort of the opposite, which is to delay slightly the audio and have the text a bit in advance and turn the model upside down such that it does text speech synthesis. So now we have a model, we can train a model with the exactly same architecture, which does speech synthesis. And so this is what we did as well, and we did that actually quite early in the project, and we had a very specific use of this TTS for Moshi. This is how we produced, I mentioned briefly that after recording 200 hours of audio with artists in studios, then we used that to synthesize way more. Well, the synthesis was based based on our own TTS. And maybe I have an example of that now. Let's see.
Hey,
Yeah.
this time I'm not chatting, but rather being controlled by text. I can express more than 70 emotions and speaking styles.
Like whispering.
Or maybe I could sing a song.
I can sound terrified.
Or impersonate a pirate, ahoy matey.
I can even speak with a very French accent, just like my inventors.
Looking forward to interacting with you.
So what you just heard is fully synthetic with the voice of this artist who gave her voice for the online demo. And so it's also to give you some intuition or feel about the level of expressivity that we can have with this TTS, which by the way is streaming TTS in real time, so you can use that on the fly if the text is produced continuously, which I will come back at the end of my presentation. All right, we can go further with having this time a script with two speakers and use the two audio channel in order to have both speakers. And this is again something we use to produce our synthetic data. And here is another example now with two speakers.
Do you watch drama series? If so, which one?
Yeah, I do. There are so many good ones out there.
Can you tell me about the one you watch?
Well, one of my favorites is Perry Mason.
Ooh.
Yeah, it's an American legal drama series. It's original.
Let me stop here. And now I'm moving further with something even more radical. We can use this architecture for translation. So in that case, the input audio stream is the source language speech by a user. In this case, it's in French. And then we can use the two other channels to have speech-to-speech translation into English and also a speech-to-text translation in English using both the audio and text output channel in green and gray here. And this is done on the fly, so we can here have a simultaneous or interpretation system that can run in real time on the fly. On top of that, we are able to some extent to preserve the voice of the input source. So it's essentially real-time simultaneous translation with the same voice, which is obviously very useful for many use cases again. And the prototype, which has been released, is from French to English. And another very nice aspect of this model, which is called Hibiki, and which is which has been developed in particular by Tom Lagios, a PhD student and former master student with us. We just presented his work last week at ICML. Is that the model is small enough, at least the smallest version, to run on actual mobile phone without any connection, so fully locally. And the small video that I'm going to show now is an example of this use case. The audio output has been re-injected in the video for the clarity, but it's exactly on the same. I mean, it's exactly the speed at which it runs.
Bonjour à tous. Je suis ravi de pouvoir m'adresser à vous aujourd'hui en français.
Hi everyone, I'm delighted to be able to speak to you today in French since my phone will translate what I am telling you into English. As you can see, it is in airplane mode. It doesn't have an internet connection because our machine translation model allows for real-time voice translation entirely on the phone. You can find the model for free download on Hugging Face or on our GitHub.
Let me stop here. So so it does make the point that it runs on the mobile. The mobile version is slightly less good at preserving the voice, but it tried to imitate it to some extent. In any case, adapts to the input voice. And also maybe you notice that the delay between the translation and the source is variable, which makes sense, is exactly what happens with a human interpreter, because sometimes you have to wait more content in order to do a confident translation. In order to train this system, we needed actually this type of data with French audio and English audio translated with variable delay based on the content. And for that, we had a semi-synthetic approach where the input, the source French audio is real data that we transcribed, translated in text, and resynthesized in English with this variable delay based on some probabilistic or statistical criteria based on essentially on the likelihood of the next token in the translated version. And based on that, we could train Hibiki with sentences which are up to 2 minutes, but there is no limit on the at runtime, and also the time context for the transformer is 40 seconds. All right. So as I said, you can use Hibiki has been released in 2 sizes. The one I showed on the mobile is 1 million parameters. Another aspect which is very nice is that the fact that because of this very regular and simple in a sense multi-stream architecture and streaming architecture, this allows us to batch a lot of distinct conversations or translation on the same GPU. So typically on a high-end H100 GPU, you can have more than 300 translations in parallel, which is very important for the efficiency and the cost and compute efficiency of the model when if you want to serve it offline or online, sorry, in the cloud. So yeah, everything is on our GitHub and Hugging Face space, so you can give it a try, and we're happy to get feedback. As I said, Moshi is very robust to environment noise, while Hibiki inherits the same properties, and as I'm going to demonstrate here now with another interesting snippet of Alexandre Desfossés celebrating the public demo of Hibiki at the AI Summit in January.
My name is Alexandre, and I am testing this model in extreme conditions. At this moment, there's very loud music, and I can barely hear what I'm saying. However, our model is able to translate live in English my voice on a mobile phone. This is a 100% French innovation that comes from our open research laboratory in artificial intelligence.
All right. Just a bit of teasing for sake of time. I won't go into detail, but we have also now a new version in a few months back of Moshi, which is called Moshi Viz. It's essentially Moshi with the ability to ingest as well visual information through visual tokens, which are inserted, which are through cross attention, which are sort of inserted in the text stream, and this allows the model to again have spoken dialogue with the user about an image or several images that have been uploaded or captured, and yet retaining the possibility to discuss of something else. So essentially, it's Moshi with eyes. And again, you can go to the web page and see some of the details. There are plenty of samples that you can play with. So let me skip the details here. But one thing is related to the training or the fine tuning. So again, we started from Moshi, and we needed some speech image conversation data, which is almost inexistent in the on internet, or also even in the academic benchmarks. So a bit in the same flavor as what we did for Moshi, we went the synthetic route by creating fully synthetic data, starting from images which are described in text using a visual language model, and then turning this description into actual multi-turn discussions between the model and a user, and then turn that into speech with our TTS. And but it turned out that we don't need a lot. It's very data efficient in that respect. A lot of the knowledge of the text-speech model and even the text-only model, text image model, transfer to speech by having only a small fraction of speech-image conversational data. All right, and again, there is a demo online which is available at viz.moshi.chat. and you can find all the details in the technical report, which is available on our webpage. All right. Now I'm going to finish with a more recent thing, which in a sense sort of closes the loop with the beginning of my presentation. I said that cascading model of audio interaction, well, it was user churn, there's an issue with latency, etc., which is true. But if you do things fast enough, it's very interesting things to do nonetheless, because it's everything being modular. You can use an off-the-shelf language model, and you can essentially plug on both sides your ASR and your TTS, which we did recently in a demo and model that we call Unmute, which essentially allows to turn a text chatbot into a voice chatbot with a very low latency, everything being streamed in real time. The latency is below 1 second. And we also, it's very flexible in the sense also that you can still prompt or provide a text system prompt to your LLM. So if you go to and I'm not going to do that right now, just to leave that for questions. If you go to unmute.sh, you will see that you can discuss with different types of personas, which have different voices and different personalities. The personality is only described or specified with a bit of text prompt. The LLM in the middle is off the shelf. In this case, it's a Mistral model, but it could be any other open LLM. And both the STT and the TTS are on. And yeah, you will see that it's quite fun to play with. You can even play with your own voice, because with just 10 seconds of audio, you can have the voice of the TTS, which is based on conditioning, which is quite resembling. All right, I'm skipping that. Just all the names of all the fantastic contributors to the different projects that I very rapidly skimmed through, and I'm going to stop here in order to have some time for questions. Thank you very much.
Thank you very much, Patrick. Very interesting, as always. We open to questions. You can raise hand and you can put questions in the chat. But maybe I would start with the first question.
Yeah.
Because we are on Atrass, which is AI trustworthiness and risk assessment in challenge context, and of course you are working on AI and on challenge context, etc. It's very clear. How could we imagine to work on the trustworthiness of such a system?
That's a very important, good, and complex question. First of all, the very big challenges of safety and trustworthiness challenges with LLMs. They essentially transfer to speech language models, of course. So there is the risk of hallucination, etc., of toxicity. So typically for Moshi, there is a large portion of the evaluation in our technical report about these things. First of all, how to evaluate the risk and the toxicity, etc., with some benchmarks from the field. But on top of that, there are speech-specific or voice-specific issues regarding the malevolent use of speech, or voice imitation, etc. So, and also voice is something very powerful. So, it's when it comes to fraud and impersonation and misinformation, etc. There is, I think, even more precautions to take with voice AI. So there are different answers to that. So it's very obviously very challenging. There is it's an open question. One aspect has to do with same with images, by the way, has to do with marking the generated contents or storing or marking in some way, but in order to at least after the fact or post hoc to be able to prove or to establish that something is synthetic as a way to limit the bad usages of the voice technologies. So it's something which already exists, including from state-of-the-art and cutting-edge players in the field, like people providing speech-to-text, text-to-speech, like voice synthesis. So there is a lot of precautions around voice cloning and the like. So this applies as well to what we do. I think at the end of the day, there is always something very important, which is communicating and broadly about both the dangers and the risks associated to this model. So I think there is a more educational and pedagogical answer to this question, which is at the society level. And then there are other questions related to explainability, transparency of these large models. So it's very complicated because I think the field is fairly nascent. I mean, explainability of these large models, but it's all these questions also related to copyrighted material.
I'm doing like Moshi, I interrupt you in the middle. And I think, in fact, it's good for us because then it means that we will have a lot of research to do in the next years.
Yeah.
So it's good for the researchers. Yeah. It's a lot of things to do. I'm seeing...
Go ahead. Yes. Go ahead. No, go ahead.
I see Suyan Sai, who has a question, please.
Yeah, thank you very much. That's a really, really interesting demo, and I'm looking forward to trying out Moshi. I have two questions, if it's okay. Sure. The first one, so I see that in your technical paper, you've done a lot of evaluations, and you've used for the text part a lot of standard benchmarks. Do you, for the speech part, believe that the existing benchmarks are good enough, or do you see some directions where people should go if you want to develop new benchmarks purely because you're kind of introducing a new class of models? What do we need here?
Well, I think
these. Yeah. Maybe the second question as well. You mentioned about the cascaded models being more robust, or not robust, but they might have lesser hallucinations than your approach because you have really 3 streams. Do you have some kind of analysis on where particularly they deviate? For example, the text stream and this voice streams, or is it some analysis that's more for the future?
Okay, regarding the first question, so I think already evaluation of general purpose LLM is not satisfactory, but because it's because general purpose tools are very hard to assess in real world usage. But I think it's already not satisfactory. So with speech-based language models, we have the same problems, but even worse, because a lot of the benchmarks, they are based on text. So before, in order to assess or to compute the metric of the voice model, you need to first transcribe the answers to text. So then there is some noise, etc. So that's one thing. But overall, I think as soon as you deal with conversational multi-turn discussions models, whether it's written or spoken, it's difficult. I think the metric, they are not, apart from going to user test with arenas or these kind of things, or using other LLMs as a judge, etc. But I think, evaluation, it's something that we are, as scientists, or computer scientists, we are not yet completely used to, or we are not very comfortable with, is how to assess the utility, the accuracy, etc., of dialogues in general purpose context. Of course, if it is to solve a math problem, it's easier than. But if you want, a discussion it's another story. So that's one thing. So definitely we need more benchmark, especially for when it comes to voice AI, conversational for more specific tasks like transcription. The metrics are pretty clear. Synthesis, some of them are more subjective, but for transcription, I mean, you need the transcription. There is one ground truth, right? except
okay.
for normalization. There are normalization issues, but yeah. Now to the other question. So the multi-stream version that we have with Moshi, I wouldn't say that it's more or less keen to hallucination prone compared to a cascaded model, but by training or changing fundamentally starting LLM and turning that into a more complex thing, which with spoken dialogue ability, we do lose a lot. So from the original knowledge and capacity of the pure text LLM, so we face a pretty annoying and frustrating modality gap when we go from the text backbone to the multi-stream audio or voice-to-voice model. And by losing sort of knowledge and reasoning, it means that there is more hallucination, so to speak, but it's unrelated. But that is mitigated by the fact that we have this inner monologue stream that we retain in the final system. So it's a bit like a scaffolding, right? For the cascaded model, you have the LLM that you use in the middle, so it's very modular, is essentially untouched. So if it does hallucinate, well, the hallucination will be essentially spoken, and that's it.
Yeah.
Thank you.
I see there are two questions on the chat, and I think we have to be short because we are approaching the end time for the meeting.
Yeah.
One by Clément Chotel: is it possible to put guardrails on audio-to-audio models?
Same guardrails as the one you have with the text models, meaning they are fragile. And on top of that, some of them are based on text, so you would need transcription, so not clear. I mean, it's certainly less, some of the guardrails which are used for text model couldn't be transferred as such necessarily to a voice-to-voice model where there is no explicit text involved.
Mm-hmm. And there's a question by Juan David Dugan, which is the approximative volume of training data required to support a new channel, and where he says voice plus vision plus others.
Depends for a new channel for voice, or even if you want to add another language, etc., it might be a few thousand hours. For vision, when we added vision in Moshi, the volume in audio related to images was to be checked. I don't have that on top of my mind, but it might be even smaller. But we started from Moshi already. We started from already a text speech model, and then we added the vision channel.
Okay, I don't see any hand raised, and I don't see any questions on the chat. So I'm asking my last question. If I understand well, going back to the very beginning, if I understand well, Moshi is also able to do the continuation, not only answering and dialoguing, but doing continuation. Have you experimented with people giving the continuation and see how they react?
Yeah. So you mean using the prompt being somebody? And,
I'm talking, and at the same time, the machine continues what I'm saying.
We haven't done that in real time, but we have done that in the presence of one of our French funders. And he was with his son listening to the continuation, and both were amazed, a bit nervous. And actually, I did that with both French funders and donors. So I did that, yeah.
Okay.
And both were quite impressed. It's quite weird to listen to your own voice saying things which are continued.
And as our German colleagues know, it's much more difficult for German because you have to wait for the end of the sentence to understand.
Which is for translation, for simultaneous translation, certainly something that we are curious to see how it will happen. The system should adapt by itself because we have area for that. We haven't done that yet. We'll see when Hibiki speaks translate to German and from German.
Very impressive. Thank you very much, Patrick.